Hello, my name is Kemi and I'll be talking to you today about the spinning cloth disk reactor. So the spinning disk reactor is a type of process intensification reactor where you get enhanced heat and mass transfer due to the addition of a centrifugal force. What happens is that when you add a centrifugal force into a spinning disk reactor, you actually get very thin film of liquid in the range of about 100 to 200 micrometers being formed on the surface of the disk. So these thin films of liquid are highly sheared and they have ripples being formed, so they actually cause very fast mixing as well as very short residence times in the reactor. So in this reactor we're going to be looking at a spinning cloth disk reactor, which is a piece of cloth added to the spinning disk reactor. In this case we're using a spinning cloth disk reactor for enzyme reactions, so the cloth contains immobilized enzyme attached to it. I'm looking at nylon cloth and I'll be investigating the effects of using different types of nylon material. The first type of nylon material that I'm using is a nylon carpet material, which looks like this. It's very thick, as you can see. The second type is a very thin nylon paper material, which looks like this. It's only 0.67 millimeters thick. And lastly, I'm using a nylon blanket material, which is this. All of these nylon cloths actually have enzyme immobilized on them. So the aim of this residence time distribution experiment studies is to characterize the reactor in terms of how it behaves. So does it behave as a plug flow reactor or does it deviate from plug flow behavior? So to do this, I'm going to need a test fluid of deionized water, and I'm going to need my tracer fluid. In this case, this is a non-reactive tracer and it's potassium chloride solution. It's 0.5 molar in concentration. And I need a conductivity meter, which is going to measure the conductivity of my tracer fluid at the outlet, as well as a microprobe, which has been attached to the meter and has been placed onto the side of the disc, so that the conductivity is going to be measured as the liquid is spilled off of the edge of the disc. So this setup is actually very representative of the residence time of the liquid in the reactor, as the probe is actually placed right by the edge of the disc. So in order to start the experiment, right now the nylon blanket has actually been placed in the reactor and the probe is right next to the disc. So we'll start the reactor and the flow rate has been set to 5 mils per second and the spinning disc is also set to 254 RPM. So the spinning disc reactor has been set to 254 RPM and the liquid flow rate has been set to 5 mils per second. So deionized water has been passed through the reactor right now and the conductivity is being recorded on the PC using LabX software every second. I'm now going to add my tracer fluid into the center of the disc very quickly using a pulse injection method. So the conductivity is going to shoot up, as you can see. And then the conductivity is going back down to the conductivity of the deionized water solution. So this is a very quick and easy way to determine your reactor type using residence time distribution studies. Thank you for watching and goodbye.